So here's another example of graphing a polar equation. So we have r as a function of theta. What we want to do first is to graph this function in r theta space. So we're going to have theta along this axis, and we're going to have r along this axis, and we're going to draw the graph. Now, we know what the graph of sine theta looks like, and with a minus sign in front of it, that just flips the graph over, and then the 1/2 lifts it up by 1/2. So instead of starting at 0, it's going to start at 1/2, and since it's negative sign, instead of going up, it's going to go down. So let me just graph it from 0 to 2 pi here. So I'll put in these points so we can see what they are. 3/2 pi and so on. Okay, so normally sine goes up to 1 by the time you reach pi halves, but we have it flipped, so it's going to go down 1 to negative 1/2 here. So the graph will go there, and then at pi the sign will be 0, but we're subtracting 0 from 1/2, so we're at 1/2. At 3 pi halves the sign would be negative 1, so subtracting negative 1 gives 3.5. So we'll go, let's see, yep. So we'll go up here to 1.5, and then at 2 pi we'll be back to 0 with the sign, and we subtract that from 1/2, so we have 1/2. So we've got our graph now of r as a function of theta. It's the graph of sine, just kind of shifted, it flipped and shifted here a little bit. Okay, now what we do once we have this graph is we use that as a set of instructions. Each point on this graph tells you an angle, which tells you what direction to face, and a radius, how far to walk out. If the radius is positive, you walk straight ahead. If the radius is negative, then you walk backwards from the direction that you're facing. So, okay, so first, facing direction, an angle of 0, we walk forward 1/2. So facing out the positive x-axis, we're going to walk here forward 1/2. Let's see. Facing due north, so facing pi halves, we're going to walk backwards 1/2. So we're looking up the y-axis, but the radius is negative, so we're going to walk backwards in this case. Let's see, at pi, we're going to walk forward a step. So facing pi, that means facing west or looking back along the x-axis. So looking in this direction, we walk forward a step. So we end up here. Facing 3 pi halves, we walk forward a step and 1/2. So 3 pi halves is looking south. So looking south this way, we walk forward, 1.5. So there's 1/2, 1, 1.5, so we walk forward to that point. Okay, and now facing 2 pi, so we're back facing down the x-axis, and we're back to where we started. We walk forward 1/2. We need to fill in a little more detail here before we can figure out where this curve is. So let's look now at maybe this angle. This is the angle pi force, and looking at it, looks like we're going to be taking, facing pi force, we're going to be taking about, let's see, a 1/4 step back. So facing pi force, which would be looking in this direction, we're actually going to take a 1/4 step back. Okay, so and we've got a similar point here. This is 3 pi force. Facing 3 pi force, there's a symmetry there, so it should be about the same value, even if my graph isn't so good. Okay, so facing 3 pi force, we take about the same distance back. So we're looking out this way, but we take about a 1/4 step back in this case. All right, that's starting to fill in maybe a little bit of detail. At some point, we're back at the origin, huh? So as we're turning from 0 to before we get to a 1/4 pi, we actually are at 0. So let's see, that means that as we turn back, the radius is slowly going negative. Alright, all in this region. Although we're looking out into the first and second quadrants by these angles, we're walking backwards into the third and fourth quadrants. So we come around here. Even though we're looking out over here into the first and second quadrants, we're actually going backwards. Just interpreting that from the graph here. Let's see. From here, we have 0. We're back at the origin, and then we slowly turn till we're looking towards pi, till we're looking to the west, and our radius gets longer and longer. So as we slowly turn, we're looking in these angles, but we're able to step out further and further and further until by the time we're facing pi, we actually get to take a full 1/2 step out. Okay, now from pi to 3 pi halves, you see the radius is gradually getting longer. So as you're turning from looking west to looking south, the radius is actually getting longer and longer as you go out like this. Okay, and now as you turn from 3 pi halves to 2 pi, the radius is gradually getting shorter until it's 1/2. So as we turn, we're looking out in this direction, we have positive radii, so we're actually walking out into the fourth quadrant. And the more we turn, the less distance out we can walk from the radius. So initially we can take a whole, when we're facing south, we can take a whole 1.5 steps out, but then we can take less and less and less, so we get this shape. This shape's actually called a limacon, which is an old French word for a snail. So it looks a little bit like a snail with this inside loop. Notice that whenever you go from a point where the radius is 0 to another point where the radius is 0, that creates the loop. So because you start out, if the radius is 0, you're at the origin, then you have some time where you can get away from the origin, but then you're back to the origin. That's what's creating this loop right here. This space here, let's see, if we were to continue on out here with our graph, let's see, by the time we got to 2.5 pi, we'd be down here again. So you can see from here to here, that is creating this loop here, the big outside loop thing. Oh no, that's, yeah, until we get to that point, right, where we come back to the origin. So we're creating this loop here in that region. Okay. Now, this graph, if you notice, actually has symmetry around the y-axis. When you look at the graph, you could shift it around the y-axis. So how could we tell by looking at the function that that symmetry would have to be there? Well, when you know it's there, you know that the function really can't tell its left from its right. And let's consider 2 points on either side of the y-axis. This point, let's say this point is at r theta. What would the coordinates of this corresponding point over on the other side of the y-axis be? Well, one way to get there would be to go, instead of just turning the angle theta, you could turn a whole angle of pi and then back off theta, and then you'd be here. So one characterization of this point is r pi minus theta. Another way, and there are many, many ways to get there, but another characterization of this point that's on the other side is that if you, instead of turning theta, instead of going this way with the angle theta, you went in the opposite direction with that angle theta, then walked backwards, you could get to this point here. So another way that this point is related to the point on the other side is that if this point's r theta, this one is minus r minus theta. And so if you have a function that can't tell the difference between r theta and r pi minus theta, or if the function can't tell the difference between r theta and minus r minus theta, then you know it's got symmetry around this y-axis. Now notice the sine of pi minus theta is actually from the angle difference formula, the sine of pi times the cosine of theta minus the cosine of pi times the sine of theta, which is, let's see, the sine of pi is 0, so this is 0. The cosine of pi is -1, so we have negative sine theta, so that's equal to sine theta. That means whether or not you give this function the angle theta or pi minus theta, this function can't tell the difference. So if r theta satisfies, so if it satisfies the equation r equals 1/2 minus sine theta, then r pi minus theta also satisfies the equation, because the sine of pi minus theta is the same thing as the sine of theta. That means that this function can't tell the difference between the right and the left, and that means that even without graphing it, you know that this function is going to have a symmetry, so that any point on this side will have to be on this side, because any point on this side that satisfies the equation would automatically have to, if a point on this side satisfies the equation, the one on the opposite side automatically has to satisfy the equation as well. The equation can't tell the difference between the two. So this is a characterization of a second kind of symmetry. We already saw that the condition that two possibilities where a polar function might not tell the difference between above and below the x-axis would be if it can't tell the difference between r theta and r minus theta, or if it can't tell the difference between r theta and minus r pi minus theta. Then it's going to have symmetry about the x-axis. Now, the problem here is that polar coordinates aren't unique, right? So there are other characterizations of that symmetry. So just because a function doesn't have this property doesn't mean it doesn't have that symmetry. But if it does have this property, then you're guaranteed it does have that symmetry. We just saw in the last case, symmetry around the y-axis. If the function can't tell the difference between r theta and the point on the other side of the y-axis, r pi minus theta, or if it can't tell the difference between r theta and this characterization of that same point, then it's going to have that y-axis symmetry. There are other characterizations, so this isn't an exhaustive list. It's just a few that you could check to know that you have that particular symmetry.